All right, let's talk about acids, bases, and salts. We're going to do a quick intro into some basic properties. Haha, get it? Basic? Yeah, you know, okay. Anyway, this is give you some context and why you need to have a little bit of information about acids and bases. There is this place called Bracken Cave, and it has 30 million bats, and you can go visit that. But in order to visit it, you have to be very, very careful because it does have ammonia, a lot of ammonia there, and it is a weak base, and it's a byproduct of their urine, and if you're not careful, that can affect your lungs because you breathe it in. All right, so let's keep going. Let's start first with our acid properties, just cover some topics in there. We're used to thinking about citric acid, like in lemons and oranges. That's the easiest way to remember it. It tastes sour. We've done that for a while now. When you have indicators, which we'll talk more about those later, indicators, acids will change the color of an indicator, and it's all going to depend on the pH. Now, the cool thing about indicators is, now this is a rainbow of what we would call a universal indicator. It's a mixture of different indicators, and depending on the pH, you'll get a different color, and you can qualitatively get quantitative results. I know it seems kind of contradictory, but qualitatively you look at the color, and then from that you can extrapolate a numerical value. And it does have some error associated with it, so it's not ideal. So you get mostly qualitative data from that with some quantitative results. I know it's odd. All right, let's talk about ionization of acids. There's different types. We have strong acids. Now, a strong acid is something that is going to be very reactive. The reason why it is very reactive is because it is a strong electrolyte, and that means that it has ionized 100%. All of the H pluses on the acid have broken off, like you see in this picture here. So here we have some hydrochloric acid, and it's a covalent compound. But as soon as you dissolve it into water, you get your little hydrogen ions and your chloride ions, and they have ionized and broken apart. And this hydrogen ion is super duper reactive, and that's what makes it a strong acid, all of those little H pluses floating around. And because they're strong electrolytes, it's very conductive as well. Alrighty. Keep going with that. Now, as far as the strong acids are concerned, how do you know when you have a strong acid? Well, it's easy. There's 7 of them. You just memorize them. That's all you have to do. So, here's the list. And yes, you are expected to know these 7. Now, if you take a look, it's not that bad. Here we have HCl, HBr, HI. They are all in the same family. These are all of our halogens. Like group 17, Cl, Br, I. Not HF, though. Hydrofluoric acid is a weak acid, so don't be confused. It's a little tricky. That fluorine, even though it's more electronegative and that bond is weak, and you'd expect that hydrogen to go flying off, it's so small that bond strength is really, really strong, so it's not a strong acid. So we only have our chlorine, bromine, and iodine as our strong acids. And then you get to the chlorate, HClO3 and HClO4. So those are 2 of our strong acids. And then these are your little anomalies that don't have any pattern necessarily that you recognize yet. So we have nitric acid and sulfuric acid. This is one of our only multiprotic acids that is a strong acid. So if you have all 7 of these memorized, anything else that we say is an acid is weak. Alrighty, so let's talk about those weak acids. They are weak electrolytes. They only partially ionize in solution. What does that mean? Well, if you take a look, here's an example. Here's that hydrofluoric acid I mentioned. When you put it into water, some of these the hydrogens on the hydrofluoric acid will come over to the hydronium ion, and you'll get some fluoride. But notice the arrow is not one way. So as soon as you make it the H plus in the form of hydronium, it's going to go back and reconnect with its fluoride partner and make some more hydrofluoric acid. So it's this dynamic equilibrium. And so when we look at this picture here, what we have is, here's your hydrofluoric, here's your H plus, here's your fluoride, and macroscopically we see that there is no change. It just is, on the microscopic level, it is a dynamic equilibrium going back and forth between the molecular form and the ionized form of your acid. All right, let's move on into electrolyte action on your notes. Acids are electrolytes. Whether they're strong or weak depends, but you will always have ions present. That's easy. And so you will conduct. Whether strong or weak, that depends on the acid. Moving into reactions, some very basic reactions for acids. And you've been learning this one for a while. They will react with bases. It's called a neutralization reaction. It's just another form of a double replacement reaction. It's a more specific type of double replacement. And we form a salt and water. And you've probably seen it before, but here's a classic example. Hydrochloric acid with sodium hydroxide. The sodium and the hydrogen trade places, and you're going to end up with sodium chloride. There's your salt and water. Now what's the driving force with this double replacement? Unlike the last unit, which we were looking at solids a lot, this one is the formation of a pure liquid. Remember, double replacement, solid, liquid, or gas formation is the driving force. So for neutralization, it's the formation of this pure liquid that's the driving force. So there's our salt and our water. Another type of classic reaction, and you guys have seen this in the lab, is they will react with metals to form hydrogen gas. And we did this reaction in the udiometers. And so here's our magnesium and 2 HCl's, and this is a single replacement reaction. Magnesium trades places with the hydrogen. You get your magnesium chloride and your hydrogen gas. And this was from our lab where we determined the molar volume of hydrogen. So you have seen this in person. Alrighty, that's a little bit of a summary of acids. Let's move into bases. For bases, taste, bitter. Just think about soap. Hopefully none of you have had your parents wash their mouth out with soap. I doubt you, because you guys are wonderful. Indicator, exact same answer as acids. They will change the color of an indicator. It's just going to give you a different color, that's all. And again, it's qualitative data with quantitative results. And we'll get more into pH next week, but for pH of a base, it's going to be more from 8, 9, 10, 11, 12. That's going to be your basic range. Ionization, you have strong bases as well, just like we had strong acids. And they are 100% ionized. That's why they're strong electrolytes. And one of the simplest definitions of a strong base is that when you look at the formula, it has hydroxide ions. And this isn't always true, but for now, that's what we are going to go with. So you're going to look for the hydroxide ion. So for example, if you look at this picture here, here's your sodium hydroxide. There you go. And you get your, when you dissolve it, you're going to get your hydroxide ions in solution. So that's why it's a base. We get that hydroxide going. And this is just a molecular view, so there's the hydroxide as well. Ionization. We do have weak, bases. Weak bases are weak electrolytes. They're partially ionized, but they make hydroxide. So a classic example of a weak base, like we've seen already, is the ammonia. When you put it into water, it will make hydroxide. It doesn't contain it, but it reacts with the acid to make hydroxide, and we see that here. So what will happen is one of these hydrogens in the water comes over to the ammonia, and you get this hot ammonium ion and the hydroxide ion. So that's what makes it a weak base. And they're all together. And notice we do have this double-sided arrow again. Weak gets that double-sided arrow, so it's in equilibrium. And as far as electrolytes, they are electrolytes in aqueous solution because we get ions. Again, just like acids, so very similar. As far as reactions are concerned, bases, exact same thing. If the acids react with a base to make salt and water, bases react with acids to make salt and water. So it's the exact same thing. And this is just a little graphic of the same exact reaction we saw with the acids. Okay? Now when this word destroy, neutralize. Essentially, you will no longer have an acid or a base when you react them together. This is a little graphic for you. So we're going to examine the behavior of an acid in aqueous solution. So here we have acids, HA, and so the little purple one is your hydrogen. If we have this in solution, what is going to happen? Well, with a strong acid, notice, do I have any of the HAs together? No. I've had all the hydrogen little purple spheres break apart. They have ionized, and so it's 100% ionization. So we have all of our ions broken apart in a strong acid. Would the solution be conductive? And the answer is absolutely. You have lots of ions in solution and conduct very well. A weak acid is a little different. Notice, yeah, they're highlighting these so you see them. We still have a lot of the molecular acids stuck together. Those hydrogens are still connected, so they're not going to react. But these three that are flashing, notice that they have broken apart. And so we have some of our molecular acid, some of our hydrogens, and some of our conjugate bases. This would be your weak acid. And you get partial ionization. And it would be conductive, but not as well as a strong acid. Now, oh no, it's switched. What? So those three that were flashing before are now molecular. They reattached, notice, and now we have three other ones that have ionized. So it is a dynamic process. So you'll have some ionized, some molecular. They'll switch, and it's constant, back and forth. And this is a little picture here you see. They are constantly going back and forth, back and forth, back and forth. And at any one time, only a fraction of them are ionized, just like you see in the picture. So I have 3 out of, I don't know how many that is, like 20. And that'll be the same fraction for any particular acid. All right, that's a basic review. Keep doing it, get it, basic. Let's move into some very quick different types of theories on how we define acids and bases. We have Arrhenius. This is your classic one that you're used to thinking about. I don't know if you knew the name of it. And then we have Bronsted-Lowry. And we also have a Lewis acid and base, but we are not going to cover it. Okay, so we're only going to do 2 today. Arrhenius definition. This is your classic one that you are used to thinking about. Acids make H+. So here we have our hydrochloric acid making H+ and Cl-. So you're looking, the thing, it has to be in solution. Water has to be present. Very limiting, very specific. You have to be making H+'s in a solution of water. And for bases, they contain or make hydroxide in a water solution. So very limiting. Now, what we found out over time is that not all acids have H+, and not all bases need to have hydroxide either contained or made. So we moved on from Arrhenius after a while, but this still applies to a lot. Just to give you some examples of Arrhenius acids, example 1, we have a monoprotic acid. This is something that releases only 1 proton, 1 H+ into solution. And classic example, HCl going to H+ plus chloride. And here you have a molecular view. So you have your HCl molecule, some water. Now remember, it doesn't just form H+. This is just a simplified version. What actually happens is a little chloride here, or not chloride, a hydrogen here gets, so backwards here. This hydrogen here comes over and is attracted to that oxygen, and so we end up with the H3O plus hydronium ion and the chloride ion. Second example, a diprotic acid. This is going to be 2 protons, 2 H+'s released into solution, and our strong acid sulfuric does this. So it actually undergoes two ionizations. It will release the first hydrogen, and you're left with HSO4 with a -1. And then once this is formed, this will undergo a second ionization. And it's a weaker. Notice the arrows both ways. And this is just a molecular view of sulfur. So those are some classic examples of Arrhenius definitions. We do have triprotic acids. They're not strong. They do exist. For example, a phosphoric acid. It does have 3 protons here. Not all 3 are usually released though, but you do see that sometimes. And so those 3 protons are bonded to oxygens, and those are what come off with your triprotic acid. Let's move on to bases, and then we are pretty much done, I believe, with a little bit more of it. Oh no, we have Bronsted-Lowry. Example 1, potassium hydroxide. It contains hydroxide, so that's definitely going to be a base. And your formula, you have your potassium hydroxide. It dissociates into potassium and hydroxide. And you can write these equations in your sleep now after the last unit. And then we have ammonia. Now notice it doesn't contain hydroxide, so it's going to make hydroxide. And we already saw this. One of these hydrogens in the water comes over to the ammonia, and here we have the hydroxide made in solution, so that's why it's a base. So this one would be a strong, and this one would be a weak base. Let's move on to Bronsted-Lowry. So we didn't want to be limited by water, and Bronsted-Lowry allows us to not be limited. The definition for an acid for Bronsted-Lowry is it donates an H+, and bases accept an H+. So notice there's no hydroxide mentioned. That's the big difference. And ammonia not only fits the Arrhenius definition, but also fits the Bronsted-Lowry definition. And water is the same. So if you take a look here, water is donating a hydrogen ion over to the ammonia. Well, according to Bronsted-Lowry, donating a hydrogen ion, that makes it an acid, so it's a Bronsted-Lowry acid right now. And then the ammonia, since it's accepting an H+, it makes it a Bronsted-Lowry base. And this is just different ways to look at the reaction. So if we take a look at, let me change the color of my pen real quick. So we take a look at this nitric acid and ammonia example. What is going on is the nitric acid is taking this hydrogen and it is coming over to the ammonia. So it's donating an H+. So it is a Bronsted-Lowry acid. And then the ammonia is accepting that H+ to become ammonium, so that's a Bronsted-Lowry base. That's how you look at it. Alrighty, now this is, I think, one of the last things we're going to talk about, conjugate acid versus conjugate base. This word conjugate just means something that's kind of opposite but paired up. So when we talk about a conjugate base, the definition is what's left over after an acid loses its H+ ion. You're going to be looking for things that differ by a single hydrogen. A conjugate acid is what's left over after a base accepts a hydrogen ion. So conjugate base goes with the acid. Conjugate acid goes with its base. And then if you can identify those, we have these conjugate acid-base pairs. Like I said, you are looking up for, in a chemical reaction, two things that differ by a single hydrogen ion. So if I were going to be looking at this reaction, so here's acetic acid and water, and this H+ here is coming over to the water. So this is going to be a Bronsted-Lowry acid, that's a Bronsted-Lowry base. When I look over in the products, which one of these differs by one hydrogen with the acetic acid? Well, it's going to be here. This is the acetic acid, and it is paired up with the acetate. So those two are our conjugate acid-base pair. You have a second acid-base pair with the water and the hydronium. They differ by a single hydrogen. So let's go ahead and do some examples. So you'll get these reactions, and you're going to be looking for things that are going to differ by a hydrogen. And so we have this aluminum hydroxide, that's a base, and hydrochloric acid. Now don't be confused, this aluminum is going to be not really part of the acid-base reaction necessarily, so we're looking at the hydroxide here. So here we have hydroxide. What happened to the hydroxide? Well, it came over, got a hydrogen from the hydrochloric, and became water. And what happened to the HCl? Well, it lost the chloride, so that went into the aluminum chloride. And so we have two different sets of conjugate acid-base pairs. So the OH in the aluminum hydroxide became water, and the chloride, the HCl, became a chloride ion in the aluminum chloride. Let's do a couple more. Okay, so this is our base, and this is its conjugate acid. This is our acid, and that's its conjugate base. Ammonia. So here we have, I'm going to go ahead and circle it, we have ammonia. And we look over here, which one differs by one hydrogen? Right here. So that's a conjugate acid-base pair. And then here's water. And its partner is the base, the hydroxide. So the ammonia here is your base, and its conjugate acid is ammonium. This one is reacting as your acid, and its pair is the base, conjugate base. So that's how you do it. Taking a look at this one, same thing. I see hydroxide here, and I'm looking at the products, and there's water. So these two are a pair. So this is a base, and it's conjugate acid. So this is sulfuric acid, and notice over here, those hydrogens are gone. It became potassium sulfate. So this is our acid, and this is the conjugate base. It can look a little complicated sometimes, but this is your acid, and I know that because that's the base. So you get to see a pattern. Hydroxide becomes water. So hydroxide is our base. Water is the conjugate acid. This is acetic acid, and there's the acetate ion. So here's our acetate and conjugate base. Well, don't worry, we'll review more of this in class as well. Just to kind of bring it together, Arrhenius is an H+ producer in solution with water, OH producer for a base. Bronsted-Lowry is an H+ donor, H+ acceptor, and you do not have to be in water. And Lewis, don't worry, but there it is, and we are done. So don't forget our homework this weekend, QFT assignment in Google Classroom. That's just the writing assignment. You're going to go ahead and pick one of those top 3 questions in our shared document. Pick the one that's most intriguing to you. Do a little bit of research and write a quick one-page double-spaced writing assignment to research one of those questions. And then Unit 8 vocab is going to be stamped on Tuesday, but go ahead and do that and have a fabulous weekend. The end.